model consists of PV battery with bidirectional converter. This is a control for this battery. You told me that you are implement two cases. One is case 1, nothing but varying irradiation condition. Case 2, nothing but varying load condition. This constant block used for selecting the case 1, case 2, and you are going to put 0 here. This simulation will be operated at case 1. When you are going to put 1 means a simulation model will be operated case 2. In case 1 condition, we are measuring the PV current, and then that going to be converted into 1000 amps scale, and it going to be compared with the reference current. That means some current not to get the logic. That means when there is low irradiation condition, battery should be discharged. When there is high irradiation condition, battery should be charged condition. For that, we created this logic. Based upon that PV current, it will be generated the reference current. Not to battery goes for discharging mode to charging mode based upon this irradiation condition. And also here for case 2 condition, here we are measuring the load power that going to be converted into current. Here also we have created some logic. When its load is very high, battery goes for the charging condition. When load is very low, battery goes for charging condition. For that, we have created this logic. Here, the based upon load power, it will generate the reference current for discharging and charging of battery. Here we have switch. The switch is for selecting the mode when based upon this value. When equal to 0, it will be allow this reference current. That means case 1 reference current. So when change the constant equal to 1, it going to be allow this reference current allow. Based upon this case 1 and 2, the reference current will be changed. So finally, here we will get reference current based upon case 1, case 2. It going to be compared with the battery current, and it going to be processed by a PA controller. It will generate the cycle. When we process a generator, it will generate the pulse. This pulse will be given to this 2 IGBT, not to charge the battery and discharge the battery based upon the reference current of the case 1, case 2. Here we are measuring the battery power. Here we are measuring the battery current. This is battery voltage. This is source of the battery. Okay. And here we are measuring the power of the PV panel. Here the power ratings mentioned is in terms of 100 kilowatt. Here I am going to mention 20. So 20 into 100, 2000 kilowatts. So totally 2000 kilowatt, like 2 megawatt. Outline voltage of the unit side will be 400. Frequencies we are going to consider as 50 hertz. This is nominal power 2 megawatt. This is the PV panel rating. Here you have to put 20, and then we will get the PV characteristics. You can see here the maximum power is around 2 megawatt. We can change the detail. This is detail also. You can see the PV characteristics per different irradiation conditions. Here you can see that the maximum power is around 2 megawatt. This is a rating of the single panel. Maximum power, circuit voltage at max 4 point, current at maximum 4 point. Here in this, the model is inside that block. That's why you are not get the result initially. That means P mode nothing but you have to take the value from here. This is P mode. That value should be here. Then only you can see the plot of IVPV for different temperature and irradiation condition. Next, the battery is connected here, like in this point. This point is battery connection point by a bidirectional converter. Same point here, battery connected here. We have this link, and then this is inverter, and then this is LC filter, and then this is step-up transformer, and then this is inverter control. So inverter control have P and MPPT. P and MPPT receive two inputs, PV, voltage and current, and it going to be processed. This is PO MPPT, basic P1 PT. It going to be generate the reference voltage. This reference voltage going to be compared with the DC link voltage. This is the DC link voltage. It going to be measured here. This voltage, the DC link voltage measured here and processed via PA controller. It going to be processed by the PA controller. This is the voltage regulator. It will be generate the ID reference. This is ID reference current, and here we need to measure the voltage of grid inverter and current of the grid inverter by using here we are converting that the solar DB grid inverter voltage into per unit value, and then here getting omega t. Here we are converting that ABC to DC not form, and here we are taking only VDVQ and IDIQ, and here we have that reference current ID reference. This is IP reference. So inside this is feed forward compensation control. Here we are comparing IDIQ reference with the IDIQ actual and process the PA controller. It will generate the control voltage. This is feed forward common shifting. This is also generating some voltage. Finally, you have to add both this voltage output of PA controller and output of feed forward compensation. Finally, we have VDVQ control voltage. After that, here we need to convert the VDVQ into actual ABC. This is a control is to for converting VDVQ into ABC. VDVQ, here you have to measure real imaginary part and then magnitude and phase angle, and then you have to use that multiplication with the sine waveform, three-phase sine waveform. Finally, you will get a ABC reference. Then it going to be processed via PWM generated block. It will generate the pulse. So this pulse going to be given to this inverter. This going to control the power flow from the PV to grid. Here we are connecting the load. Here we are connecting in the load, three loads. These two load having circuit breaker. That means the circuit breaker will be turned on based upon the case. When case 1 is executed, it going to be allow this one. That means circuit breaker always closed condition throughout the simulation for 14 seconds. When K2 is implemented, it will be allow this control signal. So in this control signal, you can see that I'm going to that means up to 4.6 seconds, the control signal will be 0. After 4.6 seconds, the control signal is equal to 1. That means the breaker will be off for from 0 to 4.6 seconds. After 4.6 seconds, the circuit breaker will be closed. Same way here, we used that step time is 9.2 seconds. Up to 9.2 seconds, the control signal will be equal to 0. After 9.2 seconds, the control signal which is equal to 1. Here you can see that up to this 9.2 seconds, circuit breaker will be open. After 9.2 seconds, circuit breaker will be closed. This circuit breaker going to be use these control steps during the case 2 condition. So this control circuit breaker always on during that case 1 condition. This is for implementing the change in load condition. Here you can see that here we are creating the change in irradiation condition. Initially the irradiation equal to 200, 1000, 1200, 200. So it will be create like this. Further you created like that. So this is for case 1. And then here we have the irradiation equal to 1000. This is for a case 2 condition. Based upon this constant, when the is 0 means case 1 condition, it will allow this irradiation condition. If constant equal to 1, it going to be allow this. And then here we have an wind turbine in generator. Rating is 3 megawatt. Here we connected that wind turbine here with the common bus. This is a default model available in the MATLAB. You can click help here. Just to copy DFIG wind turbine in the Google. DFIG wind turbine Simulink. Here you can see that we get the model detail. This is the same wind turbine model we are using here in our model. But rating will be 3 megawatt. We can go inside this model of the wind turbine. Here we are using wind turbine model and then drive train. This is a drive train. This is a wind turbine model detail. And then this is known as TFIG. It is having two winding, stator winding and rotor winding. The stator winding directly connected with the point of common coupling. Rotor winding is going to be connected to the stator via two converter. Here we are using one converter. That means this is one converter. This is another converter. Why we are using this converter? TABG will be generated 50 Hz in stator side, but rotor side this frequency will be 2 Hz. We cannot connect directly this line to this. We must convert this 2 Hz to 50 Hz. Further, you have to convert this AC into DC, and then you have to convert DC into AC. Here we are converting AC into DC from. Here we are converting DC to AC with the frequency of 50 Hz. Then we can take the power of rotor side and then feed back to the point of common cup. This is the DFIG working. These are the control already available in the AG model. This is speed regulator and pitch control. This is tilt side converter control, rotor side converter control. Everything in this MATLAB, where you just use the model from the MATLAB. It will be provide the power to the system. And also here we have diesel generator. Diesel generator we are created 5 megawatt and then 400 watt 50 Hz. Here go inside. We have two model. One is continuous model, one is discrete model. Both are having same kind of model. This is diesel generator. Both are having same model. So when you are going to select continuous model, it will be select continuous model. And when you are to select the discrete, then it will be select the discrete model. It receive two input mode and PQ WV reference. Here we have that means this is a default model created for the diesel generator. Here we have two control. So one is PQ control, another is PV control. We are going to control the power, real power as well as the reactive power. But in PV control, we are going to control only real and the voltage. Based upon mode selection, it will allow the control logic, PQ control or a PV control. And then this is nothing but the diesel engine governor control or prime mode control. This is nothing but excitation control or AVR control. This is a diesel generator is going to connect up with the common bus. Here I can choose the PV control mode, and then this is a command input for the diesel generator like PV power Q10. That means voltage reference, speed reference, power reference, and then Q reference. Here you can make 0 here. Now I'm going to submit the model. Now I'm going to submit the model for case 1. Here you can see the different scope used for measuring the PV, measuring the load, measuring the battle detail, measuring the wind. Here you can see that it will simulate for the 14 seconds. It will take 10 minutes time to complete the simulation. After completing simulation, just go to click this one. This one you will get the auto scale. You will get the full detail, that means scope detail. Same you can see that the load detail. Now I mentioning the time is 0 to 0.2. If you want to see the full scope, click this one. This is battery detail, and then this is wind generator detail. You can change the case here 1, and then it will be operate in case 2 condition. Same you can see the results after completion of simulation. Thank you.